All right, continuing on the compute theme, one of my favorite topics, we have Pavan from Samsung talking about OpenCL compute.
Yeah. Hi, my name is Pavan, as Matthew was saying. Thank you. Yeah, my name is Pavan. I'm part of Samsung Austin Research Center. And today, along with me, I have Gautam and Austin, who are also co-presenters, but I'm going to be doing the talking. Today, I'm going to share our journey towards how we are trying to make OpenCL as a first-class citizen on Android. So that's our goal. Here is the agenda for our presentation. First, I would like to give a few acknowledgements with some of the open source team members that we had worked with and teams across Google and Samsung that we worked with, and a brief recap on why we want to do this and what we are bringing to the table with respect to bringing OpenCL to Angle, and where we are at in our journey and what are the next steps that we want to take here. So here are a few acknowledgements, and I think first I would like to acknowledge the CLSPV team, and I'll tell you why. The CLSPV is also the compiler stack that we are trying to use in this CL to CLV translation. So Alan and Romerick, who worked very hard on this CLSPV team and continuously making it towards 100% CTS passing. So kudos to them. And also the Samsung Angle team or Samsung Ankle team, which is mostly the GL and the CL part of the Samsung team. Again, it's spread across US, Korea, and as well as India. And there is Google Angle team who we have Cody here representing, and there is Savash and a few other team members who are basically reviewing our code and providing feedback and suggestions based on the experience they had with Angle interfaces and making it productive. So here is a little bit of a background. So for those that have attended Vulkanised 2023, we did a talk, or Samsung did a talk, and Gabe is still here, and he did a talk where he tried to showcase the goodness of Angle with respect to having it as a replacement for OpenGL native driver and having Angle as your system graphics driver. So we want to continue on that success story, at least as Ian was saying. We shipped our S22 devices with Angle without any OpenGL ES native driver. We shipped with Angle and Vulkan as the backend. So that's our commitment towards reducing the total cost of ownership with respect to driver maintenance per se, and use Vulkan as a hardware abstraction layer and layer all these high-level APIs, either it is OpenGL or OpenCL, on top of Vulkan, so that the attack surface, if you want to think about it from a hardware standpoint of view, is only Vulkan, and we, the driver developers, will focus on Vulkan from a driver standpoint of view and make it much more robust by using these translation layers up above. So this is our continuation journey to make OpenCL also into the translation framework of OpenCL to Vulkan. Again, you might ask, why do you care about OpenCL? Again, just for those that are not familiar with OpenCL, this is a 10,000-foot view of OpenCL. Again, it is widely deployed compute-only API. I know the theme of this talks that I have heard, at least the 1.5 year, except the previous talk, was mostly graphics. But OpenCL is a compute-only API, so it does not have the baggage, if you want to call, for maintaining the graphic states and stuff that you care about. And it is very widely deployed. And there are a whole bunch of libraries and frameworks that are written on top of OpenCL. Again, it's a Khronos standard also. And there is an OpenCL working group which talks about how to keep OpenCL moving forward. And one thing which I still wanted to highlight here is OpenCL also has hooks in place by various frameworks, including machine learning frameworks like TF-Lite, TensorFlow Runtime, and the Glow compiler and the TVM compiler, all have some sort of OpenCL backends to do some sort of machine learning acceleration if you are interested in those use cases. And finally, I also wanted to say that OpenCL is definitely making a comeback thanks to ML use cases. And running ML use cases on GPUs will be a faster turnaround time when compared to your fixed function accelerators that you have on your GPUs. So OpenCL is making a comeback with ML use cases, and because of the high-level language that it provides to the end users. So having talked about OpenCL, let me give you a very high-level introduction of Angle, and I think the following slide will also give you an introduction about the Angle layer cake. So what does Angle bring to the table? It basically allows multiple flavors of operating system, either it is Windows, Linux, or Android operating system, to be able to seamlessly run OpenGL or OpenGL ES content on your native hardware implementation. Whatever is the native hardware implementation, either it is Vulkan, D3D, or Metal, you will be able to seamlessly run your OpenGL or OpenGL ES content, depending on the operating system that you are dealing with, by using this layered implementation of Angle. So it's good in a way. You get rid of your native driver of OpenGL, which might be buggy or which might have a lot of CPU overhead and things like that. And it enables you to still keep your application code as is without changing your application code. And you can just run it by using the native, either the Vulkan driver or the Metal driver or the D3D driver underneath. And what we are trying to do it is basically add to this Angle repository that is out there, the compute pieces from the OpenCL standpoint of view, so that we will be able to seamlessly run OpenCL applications on top of Angle via translating it into Vulkan APIs. So again, here is the high-level picture. From an end-user standpoint of view, you really don't care. Your OpenCL application will still be an OpenCL application. Under the hood, either you are talking to the native driver or the layered implementation. In this particular case, we want to talk to the layered implementation, translate those OpenCL API calls to VK API calls and get the job done. Some of you might have seen this slide. Again, the left part of the slide is basically your Angle layer cake, and right part is what we are trying to bring to the table here. Again, we are calling it Angle, almost native compute translation, essentially, instead of graphics. So again, it's pretty much any sort of a software stack where you have multiple layers. On the left-hand side, you have the Angle part of it, or the GL or the graphics part of it, where you have GL state tracking and GL validation. What we are adding here is all the CL entry points, or the OpenCL entry points, and the OpenCL validation that is required for these entry points. Again, the validation can come from OpenCL ICD loader layers also, and we are also adding the pieces from a runtime standpoint of view from OpenCL, and then talking to the Vulkan renderer backend using the existing interfaces that are already there in Angle, which are very well written, so that we talk to the Vulkan renderer backend, and after that it goes to the driver and gets the Vulkan API calls and gets the job done with your OpenCL application. You might ask, why do you want to add OpenCL to Angle? Again, like I said in my first talk, why do you care about OpenCL? OpenCL is a pretty good high-level language, and there are developers out there that like the high-level features of these OpenCL, like it is closer to C99. Your pointer is a pointer in OpenCL, so you can write pretty much a similar code that you write on your CPU in OpenCL. And I have a backup slide where we try to write a gem, or a generalized matrix multiplication code from CPU to OpenCL, and the port is pretty straightforward. The point is, it's a very good high-level language, closer to C99 spec. Again, there are C++ language improvements that were done in OpenCL, but it also has the C99 goodness, which some of the developers might like. And it is, of course, since it's high-level, we all had a discussion about Vulkan I'll not say lacking. Vulkan does not have the high-level language support, and it relies on HLSL or GLSL to get it into SPIR-V. So it's a good high-level language, and it can be translated to SPIR-V by using any of these open source tools like CLSPV that I will talk about in the previous slide. So it's a high-level language that can cater to any of the developers that are more familiar with writing OpenCL. And one other thing is, like I said in the Angle slide, we don't need to rely on the native driver implementation, like the legacy OpenCL driver implementation need not be there. So you can run it on any hardware or any platform or operating system that supports Vulkan as its native driver or Metal as its native driver by doing this layered implementation. And one thing that is good about compute is it's less state when compared to your graphics pipelines. So what do you need to execute a compute shader? You just need to tell the kernel that these are the resources that you are trying to work on, whether buffers or images that you are trying to work on. And if you have any constants, you'll say, these are the constants that I need to work on. When you compare it with the graphics API, you have a whole bunch of graphics state and pipeline that you need to keep track of. Key is compute pipeline is very, very little or very small, and you have less state to keep track of. And it's easier to do this translation from a compute API standpoint of view. And from a typical use cases that we have seen, OpenCL kernels are typically compiled offline. So you don't need to worry about paying the penalty of the CPU overhead at your draw or dispatch time. So all these kernels are pre-compiled in some sense, and you just take the binary and run your either some sort of a color space conversion or some sort of an ML operation, kind of pre-compiled kind of a notion. And what we are also trying to do by adding OpenCL to Angle is, we also wanted to have a non-fragmented mobile driver story by doing all the layer translations in Angle. Like I said in the previous slide, we already do GL to Vulkan translation in Angle. Now we are trying to add CL to Vulkan translation. So all the APIs that at least we as Samsung cares about, at least in our mobile phones, all the driver code and all the translation code is in one repository, that is Angle. You don't need to have a defragmented approach where you go for GL to CL or GL to Vulkan translation in one repository, CL to Vulkan translation in another repository, and so on and so forth. And it's more similar to what is to an extent done on Mesa side with Sync, where everything is in one kind of a repository. And we also think once we do this OpenCL translation in Angle, the GLCL interop for those use cases, again, on Android operating system, GLCL interop might not be much useful, but there are other operating systems like Windows where GLCL interop might still be needed. And by us doing all the code in this Angle repository, GLCL interop should be straightforward and much more easier, because both the GL to Vulkan translation and CL to Vulkan translation is sitting there in one repository, that is Angle. And again, we also will reap the benefits of open source, because Angle is, of course, open source. And we are trying to push all the code that we are trying to do with CL to Vulkan translation also into this Angle repository. So everything is open source. So again, we all talked about what are the benefits of doing open source development. I don't want to rant on that. So it's again open source. So anyone can go and get the driver. And if there is an issue, they can go fix it. So I think that's enough of a background of why we are doing and what is OpenCL and why we need to do this. Now let's talk about how we are trying to accomplish this. Like I said in the previous slide, CLSPV is the compiler stack that we are trying to use. I'll talk about the compiler stack in the next slide. So what we did is we integrated that CLSPV stack, which is again a Google-owned repository maintained by Alan Baker. And we also contributed to that repository with various features like printf and a few of the performance optimizations that we worked on. And we integrated the CLSPV into Angle code. Again, there is a little bit of a dependency with respect to the tool chains that Angle needs. So we had to integrate CLSPV into Angle code. That's already done and checked in and upstreamed into Angle code base. And we are now in the process of implementing CL runtime, that is the OpenCL runtime glue that is required to execute these CL NQND range kernel calls or CL create buffer calls onto the Angle framework, so that we have the runtime pieces in place and we have the compiler pieces in place. Again, I think I'm showing a very high-level software stack where Angle interacts with CLSPV, sends him the OpenCL C kernel that we have, gets the SPIR-V out of it, which is again representation, IR representation, I would say. And that SPIR-V is basically pumped into our backend compiler. And from the backend compiler, we get the ISA, which is the responsibility of the Vulkan driver. So here is a high-level picture of the CLSPV or SPIR-V language ecosystem. Again, I think it's pretty straightforward. It's built on top of LLVM 16 to be specific at this point in time, I believe. So it takes the OpenCL C, generates the LLVM IR from the LLVM dependency that it already has, and it does a bunch of passes. CLSPV does a bunch of passes on top of the IR or LLVM IR that is generated. And these bunch of passes are basically needed to make sure that the SPIR-V that is generated is compliant, one, with the OpenCL C specification, and two, it is also compliant with this SPIR-V that is the Vulkan specification. Again, the passes could be, one example is making sure you support long vectors, because OpenCL requires vector supports of 8 and 16, unlike the GLSL side of things. So you somehow need to support those long vector support so that you will be able to be conformant. And the other passes could be adding support for built-ins. One example of the built-in support is, again, it comes from LLVM. For those that are familiar with libclc, has the implementation of all the math built-ins, specifically your cosines, sines, or any of those operations that you care about is all coming from libclc from an LLVM standpoint of view. And CLSPV just takes that as a bytecode and uses that bytecode to do those built-in operations for us from an OpenCL standpoint of view. And like I said, our contributions to this CLSPV repository were along with the open source team members to make sure that we support printf from an OpenCL standpoint of view, and few other performance optimizations so that we'll be able to get good performance when you are doing CL build program and stuff. And one thing that I wanted to mention was, for those that are familiar with OpenCL API, the way OpenCL API gets the arguments to the kernel is via an API called CL set kernel arg. So how does this API, how does this CL set kernel arg get translated to binding is basically by kernel reflection information. So at the end of the SPIR-V generation from CLSPV, you have a kernel reflection information, which essentially tells me what are the bindings of the various parameters that you have in your kernel to the descriptors that I need to attach the resources to. So at runtime, we take this kernel reflection information that is generated by CLSPV and make sure that the appropriate descriptors have been bound to those layouts that the CLSPV has generated. And speaking about OpenCL, I think I probably mentioned this. OpenCL is pretty good high-level API. Again, it's not comparable to Vulkan with respect to some of the synchronization primitives that Vulkan brings to the table, but compared to the other APIs, it is a pretty good low-level API. So in that sense, mapping OpenCL to Vulkan is kind of natural because it has all the same concepts, like your buffers, images, and samplers also exist on OpenCL, and they also exist on Vulkan. So mapping these API concepts from one OpenCL API to Vulkan is pretty straightforward or trivial, I should say. And there are other APIs. Again, they're not the exact same one-to-one mapping, but the concepts are identical. Like the create command queue, for those that are familiar with OpenCL, pretty much maps to the command buffer or the command pool that you are familiar with on the Vulkan side. And the same is true with your CL create kernel, which is where you create your kernel object, maps to the create compute pipelines. And every command that you process, like your NQND range kernels or read buffers or write buffers, which is where the meat of the OpenCL execution happens, pretty much maps one-to-one to VK commands. So again, it pretty much maps one-to-one, and I have a backup slide where I showed you all the API mappings for those that are curious with more details. So I think I talked about the stack and how we are doing. I also wanted to show where we are on this journey. So like our target is to support OpenCL 3.0 full profile. For those that are familiar with OpenCL, OpenCL has this concept of full profile or custom or embedded profile. And it's not like you have two different specifications like OpenGL and OpenGL ES. It's all in one OpenCL specification, but you can pick and choose. Either you support full profile or embedded profile. We are going for the full profile. So you get the same benefits as you get with OpenCL on some sort of a desktop device if you want to. And one thing I should mention about OpenCL 3.0 is what OpenCL 3.0 did is it kind of said my baseline profile, if you may, is basically 1.2, and then the implementations are given the option to pick and choose what are the features after 1.2 that you want to implement. Either it is shared virtual memory, device side NQ, pipes, or whatever are the features. You don't need to go on and support all those features. You can just say you are OpenCL 3.0 compliant, which is the baseline profile is OpenCL 1.2, and then you can pick and choose what you want to support. From our standpoint of view and from our use cases standpoint of view, we don't see an immediate need for shared virtual memory or device side NQ from an implementation standpoint of view. So for this Ankyl implementation, we are not immediately going to support those features, but we might in future, depending on use cases. And prior to starting this effort of Ankyl, what we also did is we validated CLSPV to make sure that a kind of pipe clean CLSPV on our stack to make sure that our driver, either it is our driver or compiler, is essentially ready for this Ankyl or CL to Vulkan translation. So we validated CLSPV and made sure that we had an OpenCL CTS pass rate of 95%. And I think the good thing with this is we found a bunch of driver issues, compiler issues, and we found a bunch of CTS problems, as in the SPIR-V that is generated by from OpenCL to SPIR-V translation by CLSPV found some, I would say, misses or holes with respect to VK CTS, because these things are not covered from a VK CTS standpoint of view. And we are trying to write tests and fill in those holes from VK CTS standpoint of view. And again, finally, after that pre-work, I should say, we started this ankle effort, I would say 6 months ago, and we were able to achieve 50% CTS pass rate with OpenCL 3.2. Again, most of the code is still not upstreamed. We are in the process of upstreaming the changes into the Angle repository so that people can play with. But at least in our internal branch, we do have CTS passing on 3.0 with the Angle code base with 50%. Again, I think the reason why we think it is quick is because of the interfaces that are being exposed by Angle from the Vulkan renderer backend standpoint of view, which is our focus. And it made our life a lot easier to use those existing infrastructure or existing interfaces from Angle standpoint of view. And I think one thing I should also mention is, by us doing all this development in Angle, we are also relying on the testing infrastructure that is already there from test farm standpoint of view, on at least Google's test farm standpoint of view, because they're already doing the testing from Angle, that is GL to Vulkan translation already, and we are basically piggybacking on that testing infrastructure to also do CL to Vulkan testing or Vulkan translation testing by running OpenCL CTS on the same testing form. So we don't need to replicate another farm. Again, one thing I should say on this slide is this is expected performance. This is not measured with the Angle stack because we are not yet there with the Angle stack from running Geekbench compute standpoint of view. Again, this is Geekbench compute. Again, it's a compute benchmark that is out there. You can Google it and you'll get it. I think the point of this slide is Geekbench compute has two options. One, you can run OpenCL as it is, or you can also run Vulkan compute from any of these image processing operations, like your background blurs and stuff. So what I'm trying to show here is, compared to the Vulkan performance or Vulkan performance and OpenCL native performance, both Vulkan performance on this particular device is a little bit better, but the takeaway, at least I want to have, is they are comparable. So if we do a right job with translating the CL API calls to the Vulkan API calls with a little to minimal overhead, again, keep in mind the state that we need to keep track of from a compute standpoint of view is very little. So there shouldn't be a lot of overhead with CL to Vulkan translation. So we should be able to achieve more or less on par performance with respect to your native OpenCL driver stack. That's the goal. Again, like I said, this is not the measured performance, but that's what we want to achieve. And here we are just trying to show Vulkan compute is comparable in performance compared to the OpenCL legacy stack. So finally, here are our next steps to kind of wrap the effort of Angle. What we want to do is we want to achieve 100% CTS passing. Like I said, we are still 50 and we are trying to upstream the code. So we want to achieve 100% CTS passing. And again, there is work here for us to achieve this 100% CTS, which involves supporting images or OpenCL images or OpenCL samplers, OpenCL subbuffers, and a bunch of plain old data structure support from CLSPV standpoint of view or Angle standpoint of view. So there is work for us to achieve 100% CTS, and which we are working on with the goal towards being 100% CTS by our next product release cycle. That's what I'm saying in the third bullet, where we want to productize this CL to Vulkan translation on our next mobile phones. And we are also doing performance profiling while we are also bringing up functionality. And we want to achieve on-par performance with our legacy stack or native stack, because at the end of the day, if we don't achieve the performance of our native stack, it's not going to cut it with the users, or the end users, I should say, when we flip the switch to go to this layered implementation. And what we also want to finally achieve is benefit the open source community. Again, we are also making sure by open sourcing this effort, we also hope to get contributions from the open source to see if there are issues with CL to Vulkan translation that is seen on some device or our device. You're free to go download the code and change it and put in a PR request, and we will review it and get it merged. But again, making it open source, it's open for developers, and they are very welcome to change it if there is a bug that they see. And finally, by doing this effort, we wish to achieve OpenCL as a first-class citizen by using Vulkan HAL or Vulkan as a hardware abstraction layer underneath at least on the Android operating system to start with. Maybe it also becomes a first-class citizen in other operating systems with this effort. I think that's all I have. And like I said, I have a few backup slides if anyone are interested in the translations and few more details.
Great work. That's very cool.
Okay, let's try to keep this to 2 questions again, so in the interest of time. Who's got questions?
Is there any interest in supporting compiling SYCL down and running SYCL code?
No, honestly, we did not think about SYCL from an Android operating system standpoint of view. I think our goal was, by doing these layered implementations, we want to reduce our total cost of ownership from a driver development standpoint of view, and leave it up to the, again, not leave it, but open it up to the open source forum with respect to these translation layers, and we only focus on Vulkan HAL and other activities that we want to focus on. So yeah.
Nice talk and very interesting work. So obviously, if the API tests are only at 50%, and I didn't quite internalize the state of CLSPV, you said validated to a 95% level, but I'm basically asking, it's a different skill set to work on a compiler from to work on an API. And
Sure.
I'm wondering, do you see I mean, if there's another 5% of work that needs to be done to become conformant, that is compiler work.
Yeah.
Do you see that as a bottleneck? Is there a team? I don't know what
yeah,
the state of maintenance is like.
So yeah, the reason why we left that POC at that 95% from our validation standpoint of view is, yes, we found backend compiler issues, as in the SPIR-V that is generated by CLSPV is very well valid. So it's not a CLSPV bug, rather our own backend compiler bug, which our backend compiler team is working on. So that's where the rest of the 5%, which we did not validate in our POC, is. Yeah.
Right.
Thank you.